In this lesson, we'll continue our discussion of big idea number 1. What are equilibria and how are they quantitatively described? And we'll talk about learning target number 6. By the end of this lesson, you can describe weak acids and bases using Bronsted-Lowry theory. You can also determine the Ka of a system and explain its significance. And you can use the accepted Ka values to calculate ion concentration, pH, and pOH of weak acids. You can also calculate the percent dissociation of an acid. We'll leave bases for a later lesson. The Arrhenius theory of acids and bases has several limitations. It defines acids as producing H1 pluses. However, free hydrogen ions can't be found in solution. They immediately react with water and form hydronium ions, or H3O1 pluses. Arrhenius theory does not include this interaction. Secondly, it only explains acids and bases in aqueous solutions. Acids and bases can also exist in gas phase. And number 3, it doesn't explain why several compounds, such as NH3 and amines, are bases. Bronsted and Lowry developed a theory to address these problems. They define acids as proton donors and bases as proton acceptors. They recognized that acid-base reactions are reversible and describe the products by their roles in the reverse direction. The acid, after it has lost a proton, is called the conjugate base. The base, after it has accepted a proton, is called the conjugate acid. Conjugate pairs are chemicals that only differ by a proton. The Bronsted-Lowry theory describes acid-base reactions as equilibria that involve a proton transfer between chemicals. This theory accurately describes both strong and weak acids and bases. However, since it involves more math using equilibrium calculations and ice tables, Arrhenius theory is still used for strong acids and bases. It gives you the same answer but a lot faster. Here is an example of a Bronsted-Lowry acid-base reaction. If we take ammonia, NH3, that's our base. It reacts with water, our acid. The ammonia has a lone pair on it, which can attract an H plus and bond with it, making an NH4 plus and an OH, 1 minus, remaining of our original water molecule. The base, after it has accepted the hydrogen, is known as the conjugate acid. That is because in the reverse reaction, it can donate an H plus to another molecule. This makes NH3 and NH4 1 plus a conjugate acid-base pair. The acid, once it's donated a proton, becomes a conjugate base. Some compounds, like water, can donate H's and also accept them. Depending on which reaction they're in, they could behave like an acid or behave like a base. They are described as being amphoteric. Let's write some equations for acids and bases reacting with water using Bronsted-Lowry theory. If I'm going to write an equation for HF, I need to know if it's an acid or a base. It's an acid because H is listed first. It is a weak acid following rule number 1. Fluorine is one of the exceptions of strong halogen acids. Because this is a weak acid, I have to use Bronsted-Lowry theory. If it was strong, I could use Arrhenius and write an ionization equation. Because it's weak, I'm going to react it with water and make an equilibrium. Because HF is an acid, that automatically makes my water the base. When HF donates its proton, an H+, it will have left over an F with a 1- charge. When the water accepts the proton, it will become an H3O+. The F1- is known as the conjugate base. It's the acid after it's donated the proton. And the H3O1+ is classified as the conjugate acid. And here are my conjugate acid-base pairs. Pause the video and write equations for B and C. Here are the answers. CH3NH2, well, that's an amine. That makes it a base, and it makes it a weak one. Therefore, I need to react it with water and use Bronsted-Lowry theory. If my methenamine is a base, it's going to accept an H. Now the nitrogen has the lone pair to do that, so this becomes CH3NH3+. My water donated the H. It's the acid, and once it's done its donation, it will become a hydroxide ion. My CH3NH3+ is my conjugate acid, and the hydroxide is the conjugate base, because if this equation was written backwards, this would be donating a proton to that. That's why it's designated the acid, and the hydroxide doing the accepting would be the base. C. CH3COOH, ethanoic acid. That's a weak acid because it's a carboxylic. Therefore, I have to use Bronsted-Lowry theory, react it with water, and make an equilibrium. The conjugate base will be an acetate ion, and the conjugate acid will be a hydronium. Remember that very few acids dissociate 100%. This means that the forward and reverse reactions occur simultaneously, and equilibrium constants can be calculated to compare their relative strengths. The higher the value of K, the more the forward direction is favored, which means more acid dissociates and the stronger the acid. Therefore, equilibrium constants for acids are known as dissociation or ionization constants. The dissociation of a weak monoprotic acid and its equilibrium constant can be represented in the following way. If I represent my weak acid by the formula HA and react it with water and complete the equilibrium using Bronsted-Lowry theory, I will get hydronium made as my conjugate acid and A1- as my conjugate base. The equilibrium expression would be the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Now, because water is a pure liquid, it needs to be ignored in the equilibrium expression. However, if we don't take it into account, we can no longer call the constant a Kc. Because we're dealing with an equilibrium involving an acid, we will call it a Ka. Another way of looking at this is through the Bronsted-Lowry theory lens. The Ka can be calculated by taking the concentration of the conjugate acid times the concentration of the conjugate base and dividing it by the concentration of the acid. Either method works when setting up your equilibrium constant for an acid. Now we can do equilibrium calculations just like we previously did in the unit. If we're given concentrations at equilibrium, we can calculate using a nice table, we can figure out the Ka value. Or we can do the opposite. If we know the Ka by looking it up in a table, we can find the concentrations at equilibrium. Remember, because we're dealing with an acid, the hydronium concentration is directly related to the pH, using the pH equals negative log of H3O+. Let's have a look at an equilibrium calculation example. If we have a 0.1 mole per liter butanoic acid solution, we can find the pH using a pH meter. It's 2.96. With this information, we can calculate the Ka for the acid. We start by writing the equation. Because butanoic acid is a carboxylic acid, it's weak. Therefore, we have to react it with water and make a Bronsted-Lowry equilibrium. Because butanoic acid is an acid, it will donate an H+. Remember, carboxylic acids always donate the H on the hydroxyl group of the functional group. This will also produce a hydronium ion. If I start off with a 0.1 mole per liter solution, I did not add any of these two products in. I can find the concentration of hydronium at equilibrium by using the pH. To find the hydronium concentration, I would use the equation 10 to the minus pH. That gives me 0.0011 mole per liter. Now I can complete my ice table. Because I'm ignoring water, I don't have to worry about introducing anything in my ice table for that chemical. The Ka for this equilibrium will be the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients, ignoring water. This equals 1.2 times 10 to the minus 5. With an equilibrium constant this small, it's clear that butanoic acid is a weak acid. This equilibrium constant means that the reverse reaction is favored, and that there are more reactants in the system than there are products. Acid strength is also described by percent ionization or percent dissociation, where strong ones have close to 100%. This can be calculated using the following equation. The change in the acid divided the initial concentration of the acid times 100. These values can be found in a completed ice table. Here is our change in acid for butanoic and our initial concentration. So the percent dissociation can be easily calculated. This also proves that butanoic acid is a weak acid because it does not ionize anywhere close to 100%.